This is multivariable calculus, and in this video, I'm going to talk about section 16.1, vector fields. And so what we're doing here is we're really starting our last unit in this course where we start to get into a little bit more detailed applications of vector calculus. And we're not going to go too far into chapter 16 just because of the syllabus of the course. We only get so far into this, but we are going to eventually get into line integrals in a few days. And that's going to allow us to start integrating along curves. And if we went far enough, eventually we could start integrating along surfaces as opposed to what we were doing before with the double and triple integrals, where we were kind of breaking everything into those small pieces and finding volumes within those curves. Now we'll be able to sort of find an integral along a curve. Okay, so when we talk about vector fields, what we're really talking about here, and the most common one, is if you think about the gravitational force around the Earth. So that's the image that I have here. So this is an example of a vector field. So the closer we are to the Earth, the stronger the gravitational force is going to be. And that's what this is showing in a two-dimensional view. So we've got, vectors that are pointing towards the center of the Earth, but the closer we are to the Earth, the longer those vectors actually become. So the magnitude of the vector is increasing. Okay, so we've got a lot of different applications of this, but a lot of times we're going to talk about gravitational force. We'll be talking about magnetic forces. Some of you have seen this a little bit in your physics classes. So what we do in this section will be fairly straightforward because we're primarily going to be talking about modeling vector fields just with little sketches and then interpreting some of the models that you're given. Okay, so when we talk about a vector field, we're essentially just talking about a field where we've got a bunch of vectors inside the field that are typically modeled by some sort of vector function. And when we look at this, we're usually going to have components, and there will be a function for each one of those components. So I'll let you read through a lot of the details on here, but what I want to focus on primarily are these diagrams. Okay, so here's an example of a vector field. Now, this one's not quite as simple as the one that we just looked at with the Earth and its gravitational forces, but still the same idea. So we've got some set of functions that are giving us the vector components in both the I and the J directions. And you can see that depending on where we are in the XY plane, we're getting a different vector. So if we plot enough of these vectors, then eventually what we're hoping to see is some sort of pattern to this. And that allows us to get a good feel for what's happening with these vectors in this plane. Now that's a 2D view of this. There's also 3D views of this. So we can also do this in 3 dimensions. Same idea. It's a lot harder for us to draw these in 3 dimensions. It's much easier to interpret these than it is to draw them. So when you see it in 3 dimensions, it's still the same idea. We've got some sort of a function for both the I, the J, and the K components. And depending on where we are, we're going to get vectors that point in different directions and have different magnitudes. And just like with the 2D vector field, we want to try to plot enough of these vectors that we can start to see some sort of a pattern. Because typically, if we have these vector functions that are predicting these vectors at different points in space, then eventually we're going to see a pattern to our vectors. All right, so here's some examples in both 2D and 3D. Okay, so let's just go through these one at a time. So we're going to sketch a few of these. More than anything, we're going to interpret these. Okay, so here's a 2D vector field. And we've got this vector field that is 1/5 square root of y times I. So depending on our y value, that's going to dictate the magnitude of the vector. And you can see that our vectors are only going to point in the I direction. In this case, only the positive I direction, since I'm just dependent on my y. Okay, so you can see that the further we get in the vertical direction or in the y direction, the longer the vectors are becoming. Okay, so fairly straightforward. If we're along any horizontal line where the y is constant, we're going to have vectors that are the same magnitude at any point along those horizontal lines. Okay, so here's another example. We've got this vector field, negative yi plus xj. And so we've got vectors that are varying depending on where we are in space this time. And so any coordinate that I choose, you can see that we're always going to do the negative of the y. That will be our horizontal component. And the positive of the x value will be the j component. Okay, so you can see that we get essentially like a circular vector field here, where if I'm along any circle, I can see that those vectors look like they have the same magnitude. Obviously, the directions are changing, but if we were to draw enough of these in, it would sort of close in a circle if we were to choose enough points. Okay, so there's another example here in 2D, where now what we have is almost like a force that would be repelling something away. Like if you had a magnetic force where we're repelling magnetically, you can see that the closer we are, the longer the magnitude of the vector pointing away from that point. And as we get further and further away, those vectors are getting shorter and shorter and shorter. So there's different ways that we can model these things. But the main idea here is in 2D or in 3D, we're able to kind of see what's happening at different points. It's sort of like when we were doing slope fields, when we were dealing with differential equations, we have a way that we're trying to sort of indicate what's happening everywhere all at the same time. Okay, so here's another example of a 3D vector field. This one's a lot like the one we started with, where it looks like the closer we get to some center point, the more that force is acting in the direction towards that center point. Okay, so when we sketch these, you're going to do the best that you can with this. I'm not expecting it to be perfect. I'm expecting you to do your best with it. So when we do these in 2D, they're fairly simple because we're just going to have vectors that are essentially, line segments that we're going to create and then just put them in the shape of vectors. But here we've got negative y I plus xj. Remember, we saw this one up above right here, right? So this is just a small sample. It's kind of like when we looked at slope fields again. When I ask you to draw a slope field, I'm not going to ask you to draw 100 different vectors to represent the vector field. I'm just going to ask for a few sample vectors, just enough that I can see that you have a feel for what that vector field looks like. So what we've done here is just taken at different coordinates. We've taken points and figured out, okay, at that point, what is this vector going to look like? And you can see that since we're doing negative yi plus xj, you can kind of see what's happening here. So like, for example, when I'm at the point 0, 3, which is this point right here, I would have a vector of negative 3i plus 0j. And you can see that I've got a vector pointing in the negative I direction, and the length of that vector is 3 units long. Okay, so that's all we're really doing. When I'm at the point 2, 2, I would have a vector that would be negative 2i plus 2j. Okay, so pretty simple to do when it's in 2D. Okay, let's take a look at one in 3D though, because this is a little bit harder. When you start plotting these in 3D, it becomes a little bit more artistic, depending on the person, depending on how good you are with drawing these 3D graphs. You might have more or less difficulty with this. Okay, so here is my XYZ coordinate plane. And you can see that my vector field this time is given by the function zk. So whatever my z value is, that's going to be the length of my vector in the vertical direction. Okay, so for example, if I'm at, let's say z is equal to 1, and I've got a point out here, I'm going to have a vector that points 1 unit in that direction, right? Okay, so that's essentially what it would look like. Now, when I go higher up, let's say I'm all the way up here at z is equal to 3. Well, now I'm going to get vectors that are much longer, right? 3 times as long. So you just want to kind of approximate that as best as you can to be a length of 3 units. Okay, so that's the idea. Now, if I were in the negative region, this is where it gets a little more difficult graphing in 3D because it's hard to really reference where you are when you're in the negative region. But if I were to go down here in the negative direction, let's say 1 unit, then I'd have a vector here pointing down 1 unit in length, right? And so when I ask you to draw these vector fields, they're typically going to be pretty simple like this because it just starts to become a pretty big mess in 3D when you try to draw these out if you have vectors going all over the place. Okay, so we also have what are called gradient fields. So a gradient field is just a special type of a vector field, right? Because we know a gradient is just essentially representing our partial derivatives at any particular point. And what we're doing here is we're just getting the partial derivatives at any point, and then we're just going to plot those and create the gradient field. Okay, so you can see here, if I want the gradient of f of xy, then it's the x component in the I direction, it's the y component in the j direction. So then we would just plot all of those, or a bunch of those at different xy coordinates, and that would create our vector field. Okay, we can also do the same thing in 3D. Let's take a look at an example here. So it says, sketch the gradient field of this vector function x plus y, and also sketch some of its level curves. Okay, so we want to do the gradient field here. So my gradient of this function, which is a function of x and y, would be equal to, and really it's just going to be 1, 1, right? My partial derivatives are always going to be equal to 1. So let's think about our level curves first. So we know we have this vector function x plus y. So to get my level curves, I'd be thinking about x plus y is equal to k. X plus y is equal to some constant. And then we can just use different k values. So for example, if I choose k is equal to 0, well, that's just going to give me y is equal to negative x. If I choose k is equal to 1, I'm going to get y is equal to negative x plus 1. Or if I do k is equal to 2, I'm going to get y is equal to negative x plus 2. So those are my level curves. Well, it's kind of nice to have the level curves here, because then we can look at the gradient versus the level curve. Okay, so let's take a look at how this would look. I'm just going to plot this in the first quadrant. So I know that everywhere I am here, I'm essentially going to have a vector that is 1 unit in the I direction, 1 unit in the j direction. Okay, so for example, this first one at the origin would look something like that. Well, that would put me here at the point 1, 1, right? Well, the point 1, 1, I've got this line going through it right here, and it's perpendicular to my level curve, which we had talked about before with our gradients being perpendicular to our level curve. This is my level curve, y is equal to negative x plus 1. Okay, and then we can do the same thing up here. We would have anywhere along this line, y equals negative x plus 1, we'd have a vector 1 unit in length, and we'd have another level curve here, right? So we could plot a bunch of these, but you get the idea. This would be y is equal to negative x plus 2. Okay, and we could keep going with that as far as we need to go. And, you know, we'd have more vectors here. And it doesn't really matter where I put these vectors. The main thing is they point in the correct direction and they have the correct magnitude. It looks like I might have increased mine slightly, but they should be remaining constant in terms of their magnitude as I go from level curve to level curve. Okay, so fairly simple to do. Like I said, the ones I ask you to draw, they're not going to be super complicated. All right, so last thing that I want to do here is just go through a little bit of practice. This is what a lot of your homework is going to look like. Match the vector field of this vector field function xy with one of the plots and explain your reasoning. So I'm not going to write out the explanations, but we'll talk about these. Okay, so the first one we have is just x times I. So what that means is whatever my x coordinate is at that point, I'm going to point in the I direction, or the horizontal direction, at that magnitude. Okay, so pretty easy to spot for this one. You can see that when I look at, these are my 4 choices. When I look at vector field number 3, and I know this is a little bit blurry, but you can see these are pointing all, when I have positive x's, they're all pointing in the positive direction. And those directions are getting larger as those magnitudes are getting larger as the x value increases. And then when I get into negative x values, the vectors start pointing in the negative direction, and the magnitude is getting larger as I get further and further along in the negative x direction. So I would expect this first one to be vector field number 3. Okay, so I'm going to cross that one out just to make sure that we know we've used it. Okay, so let's look at the next one here. So the next one we have sine of x plus j. So you can see our x component can be positive or negative, and depending on where we are, we're also going to get, the j component is always going to point either up or down. If the y is positive or negative, it doesn't make a difference. But the x component can vary. It can go positive, it can go negative, it can be 0. We know it's going to vary between -1 and 1. So we have a lot of information about what happens with the x, and we know the j is always going to be positive. Okay, so now based on that, look at these 3 remaining vector fields and see if they make sense. So remember, our j component is always +1. So this one's possible with the j being +1, vector field 1. 2 is not possible because we've got positive and negative j components here. And 4 looks like it could also be possible because we have positive and negative, we have only positive j components here. Okay, so it looks like it's either vector field 1 or 4. Now let's take the sign into account here. So the x component can be positive or negative, right? So depending on what we're taking the sign of, what x value we're taking the sign of, we're going to see the x's varying. Well, if I look at vector field 1, that's clearly not happening. So that leaves us with vector field 4. And that makes sense because for different ranges of x values, I'm seeing negative I components. And then for different ranges of x values, I'm seeing positive I components. And then we're getting to points where we're seeing that the I component, it also looks like maybe it's hitting a point of 0 because you can see as we approach these vectors right through here, you can see how it looks like in the middle, it's probably hitting vertical. And those would be the points where the sign is equal to 0. So that's what we're looking at here. So again, it's just sort of a matter of thinking about different things that you can use to interpret this, different numerical ways to analyze it. Okay, so for this one, this would have been vector field number 4. And again, I'm going to cross that out so I know I've used it. And now let's move on to these last two. So this one for C, we have I plus j. Okay, so we're always going to have +1 in the I direction, +1 in the j direction. That's probably the easiest one here. It's pretty clear that that's vector field number 1. They always have components of 1 by 1. Okay, so this is going to be vector field number 1. And I know I've used this one now. And I've only got one remaining, so it's pretty easy to answer the last one, but let's take a look at this last one. So for the last one, we have x over the square root of x squared plus y squared I plus y over the square root of x squared plus y squared j. Okay, so the square root of x squared plus y squared, yes, it matters. But what I'm really interested in from a standpoint of analyzing which one matches up, I know this is vector field 2 by process of elimination. But I also know if I have a negative x, I should have a negative I component. If I have a negative y, I should have a negative y component. If I have positive x or positive y, I should have positive those respectively as well. And so you can see now when I look at these different quadrants on this graph, it's pretty clear that when I'm in quadrant 1, both I and j are positive, which I would expect. When I'm in quadrant 2, I is negative, j is positive, which matches up with my x and y coordinates and so on. So that's how I would match those up. So in the end here, this would be vector field number 2. Okay, so as far as an assignment goes, this is actually a fairly easy assignment because all you're really going to do is just practice with these vector fields, do a lot of matching, do a little bit of sketching. We're trying to get a feel for thinking about these vectors in both 2D and 3D. And then once we have that down, then we can start talking about the idea of line integrals.